Geerstra, an international manufacturer of valves and control technology, commissioned the world's first complete glass steam system in 2009. For the first time ever, it's now possible to look right into a steam generator and see how steam bubbles arise, how feed water is deaerated, and how the various types of steam traps really work. A number of videos take a look at important facets of the steam condensate system and its operation, thermodynamic processes taking place in the generation of steam, as well as during condensation, condensate discharge, and the origination of the water hammer effect are shown in a way that's easy to understand. This video shows the thermal processes taking place during the generation of saturated steam in a glass steam boiler. This is demonstrated with the aid of the glass evaporator built by Geerstra AG, Bremen. The evaporation process occurs at an operating pressure of 1.3 bar gauge, which corresponds to 2.3 bar absolute. At this pressure, the boiling point as well as the saturation temperature are 124.7 degrees centigrade. The capacity of the steam boiler is 50 kilowatts, which yields a steam flow rate of 80 kilograms per hour. The steam generator consists of the following components: the horizontal evaporator with a stainless steel head for the primary steam inlet and condensate outlet, as well as 16 evaporator tubes, a pressure gauge with pressure transducer and a level measurement unit employing the capacitive measurement principle in an external measuring pot, a safety valve with a blow-off pressure at 1.5 bar gauge, and a steam outlet with a ball valve made of glass. A special feature of the Geerstra steam generator is that the heating rods only act on 2/3 of the glass cylinder, with the right-hand side therefore remaining unheated. This arrangement means that it takes longer for the temperature in the right-hand part of the glass cylinder to heat up, allowing us to demonstrate some special features of the feed water supply and the evaporation process. The water starts to heat up. The thermal currents can be seen clearly. Cords can be seen moving through the water. At a temperature of about 60 degrees centigrade, the water is no longer able to hold the entire quantity of oxygen, and we observe small bubbles creating foam on the surface of the water. These consist of non-condensable gases which then pass into the gas phase, that is, the steam space. When the boiling point is exceeded near the heating rods and their PTFE supports, the first steam bubbles in the water occur there. Initially, they collapse almost immediately, but as the heating period increases, they manage to rise up into the steam space above the water surface until the boiling point has also been reached there. Because steam has 1700 times the volume of its equivalent as water, the pressure increases within the steam generator. The operating pressure is regulated to 1.3 bar gauge, so that the pressure transducer acts through the pressure controller to close the pneumatic control valve. This throttles the steam supply in the evaporator head. The steam generator is now filled with saturated steam at a pressure of 1.3 bar gauge at a temperature of 124.7 degrees centigrade. This temperature must be identical to the water temperature, otherwise no saturated steam could have been formed, and moreover, two media with different temperatures in the same vessel can lead to thermal shocks. Saturated steam is invisible. Only when it enters the atmosphere do the first steam bubbles immediately condense to form minute water droplets, which are then visible. However, this type of steam is then known as wet steam because of the water droplets it contains. At the glass surface, the saturated steam releases heat and condenses. The condensate creates a film of water on the glass surface and then flows down into the steam generator again. A major benefit of the shell-type boiler with this large water space is its ability to store and immediately deliver the steam as required, for example when there's a strong demand for steam. At a temperature of 124.7 degrees centigrade, the water in the steam generator has an enthalpy of 523.7 kilojoules per kilogram. If we now open the safety valve and extract a certain quantity of steam, the pressure in the entire system drops. At the same time, the enthalpy of the water drops suddenly, which leads to the immediate formation of steam in the water, even though no external heat was added. To demonstrate this effect, the safety valve will be opened at short intervals. Now the steam outlet is opened and steam is introduced into the glass heat exchanger. Initially, the steam condenses quickly and becomes visible, a condition which arises in precisely the same way in every steam line during every startup process. Condensate forms and is carried or entrained with the flow of steam. After a short while, the glass components have been heated up and the steam then flows invisibly upwards. Condensate drops can be seen. These are either entrained, in suspension, or flowing back into the steam generator. The saturated steam flows into the heat exchanger. In the heat exchanger, the tubes are charged with a cold medium, water in our model heat exchanger, which is then warmed up from about 15 to 40 degrees centigrade. The steam flows around the inner glass tubes, releasing its heat of condensation and forming condensate, which then falls down off the glass tubes. The condensate collects at the bottom and is discharged through the outlet. Let's take another look at the steam generator. The steam quality seems to be quite good. However, if the requirement is that only dry steam be allowed to reach the heat exchanger, a steam line must be drained every 50 to 80 meters. Furthermore, if the operational parameters fluctuate at all, it's advisable to install a steam dryer in addition. Here you can see clearly how the condensate flows along the bottom of the steam line. We will now conduct a test by increasing the level of the water in the steam boiler from 60 to 67%. Slowly, the feed water valve opens, and feed water with a lower temperature than that of the boiler water enters the steam boiler. This now mixes with the boiler water. Because the temperature of the mixture lies below the boiling point, there's no longer any formation of steam bubbles in this area. The steam boiler lacks performance, and a glance at the pressure gauge tells us that the working pressure is sinking. To counteract this power dip, the feed water in steam boiler plants is routed through the economizer, where it is preheated through the hot gases of the burner exhaust. More feed water has entered the steam boiler and the filling level has reached 65%. The first droplets shoot up in the steam dome. The steam boiler starts priming. This is a critical moment in the steam process because boiler water with a high conductivity then passes into the steam system. Priming leads to increased corrosion in the entire steam system, with all the consequences in terms of cost. To make matters worse, the steam loses heat because it's mixed with water. A kind of wet steam leaves the steam generator. This may lead to poor heating performance since the steam traps at the heat exchanger are not dimensioned for such quantities of condensate. Here it becomes clear just how important exact level measurement with only a very small control deviation is for steam boilers. An external measuring pot provides optimum measurement results. No matter how turbulent the surface in the steam boiler, the water level in the measuring pot will remain calm. Measurement takes place by means of a capacitive sensing system, delivering a stepless 4 to 20 mA signal. In this way, the water level in the steam boiler can be controlled with a deviation of only 1 to 2%. Such precise regulation is not possible if conductive level probes operating according to the on-off control principle are used. Let's now try something else. Once again, the safety valve is opened, but this time is to simulate the effect of connecting major steam users to the system. Through the increased steam consumption, the pressure in the system falls. Right away, steam bubbles form everywhere in the boiler water, this being triggered by the pressure drop and the surplus heat or enthalpy. Through the sinking pressure, the area loading on the individual steam bubbles in the water is reduced, so that these occupy a greater volume, lifting the water level as a result. This effect can also be observed in the external measuring pot. Indication errors cannot be excluded. When the steam outlet is closed again, the water level drops, since the quantity of steam bubbles in the water space quickly decreases again. In such a case, it's possible that the water level may drop below a preset limit, which will shut down the firing equipment. Here it's necessary to use a 3-component control system to consider the steam outlet, the feed water supply, and the water level in the steam boiler, and therefore prevent premature throttling of the feed water control valve. Thank you for watching.